Hi everyone. Today we are going to continue talking about radicals and continue talking about simplifying them, but we're also going to talk about multiplying radicals and adding and subtracting them, kind of like we did in the last set of notes with complex numbers. So we talked about how to simplify, multiply, add, and subtract complex numbers. Today we're going to move on to radicals and how to do all of those things with radicals. So the essential question, there are two of them. The first one is, how do we simplify radicals, just in general? How do we simplify radicals? And the second essential question today is, how do we multiply, add, and subtract? So we're going to start out with simplifying radicals because that's what we left off doing in our last set of notes. We simplified radicals that sometimes had imaginary components to them. So we're going to talk about how to do that a little bit more in the beginning of these notes. So at the last, in the last page of the last set of notes, we did problems like this, and we had square root problems and we had cube root problems. Cube root meaning the third root of something under the radical. Remember, the thing that's under the radical is also called the radicand. So, in your simplifying radicals problems, if you had a square root problem, then you had to have two of the same number or variable to take the square root. A perfect square for variables is when the exponent on the variables is divisible by 2. If you had a cube root problem, so you had a problem with the cube root of something, then you have to have 3 of the same number or variable to take the cube root. The perfect cube root is when an exponent is divisible by 3. So these are all things that we have mentioned before in class, especially when we talked about factoring using the difference of squares and perfect square trinomials, and then we talked about factoring using the sum or difference of cubes. And that's where this conversation started about a square root or a perfect square having an exponent divisible by 2 and a perfect cube having an exponent divisible by 3. So let's practice. It says, if bringing out an odd power from x, or sorry, an odd power of x from an even root radical, then you have to use absolute value around it to ensure it is non-negative. That's something that we mentioned and just kind of threw into our notes in the last set of notes, but it is something worth exploring again. So let's say that you have the fourth root of x to the power of 20. Well, whenever you have the fourth root of x to the power of 20, your base x stays the same, but 20 divided by 4 is 5. So what we've done is we've taken out an odd power, because 5 is an odd power, out of an even root. And that means we need to put absolute value around it because we don't want it to be negative. We need the non-negative answer, because if you take the fourth root of something, it's not possible to get a negative answer. So we want to make sure that this is a non-negative answer. And we add those absolute value symbols. So let's look at number 1. The same idea as yesterday. We're going to break this radical into, this is the square root, so we're going to break it into perfect squares and everything left over. 24, we need to figure out if it's divisible by any of our perfect squares. Remember that our perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Those are the perfect squares up to 100, and we listed them out in our last set of notes. So I need to figure out if 24 is divisible by any of these numbers, and all these are too big. And it's not divisible by 16. 24 is not divisible by 9, but it is divisible by 4. So 4 will go in my perfect square radical. And 4 times what is 24? 4 times 6. So that goes in the leftover radical. X squared is a perfect square because 2 is divisible by 2. And y to the power of 6 is also a perfect square because 6 is divisible by 2. So when you take your square root of 4x squared y to the 6th power, square root of 4 is 2. The square root of x squared is x. The square root of y to the power of 6 is y to the power of 3. And then we just have the square root of 6 that can't be simplified. Remember that second radical is the leftovers and it can't be simplified. And here we did take an odd power for x and y out of an even root. So we do need to put absolute value around those. Okay. So let's look at this one. This is a cube root problem. So we need to split this into perfect cubes and everything left over. Remember that variables with an exponent need exponents to be divisible by 3. And if I want perfect cubes that divide 81, I'm not going to look at these. These are perfect squares. I'm going to look at numbers that if I have 3 together will go into 81. So maybe I'm going to break up 81 into its factors. This is 9 times 9. 9 is equal to 3 times 3. 3 times 3. So here's 3 of the same number right here. 3 times 3 times 3 is 27. That's a perfect cube. And then the leftover goes in the leftover radical. X cubed has a 3 as an exponent, and that's divisible by 3, so this is a perfect cube. Y to the power of 6 is a perfect cube. Z to the power of 11 is not, because 11 is not divisible by 3, so if I bump it down until I have something divisible by 3, then that'll be a perfect cube. So 10 isn't divisible by 3, but 9 is. So Z squared will go in the leftover radical. 9 plus 2 is 11. So now, the cube root of 27 is 3. The cube root of x cubed is x. The cube root of y to the power of 6 is y squared, because 6 divided by 3 is 2. And the cube root of z to the power of 9 is z cubed, because 9 divided by 3 is 3. And then we have times the cube root of 3z squared. Okay. Remember on problems like number 3, this is imaginary. The square root of a negative something, that makes this an imaginary answer. So I'm going to break this into -1, the square root of -1, and the square root of 40. You learned in the last set of notes that the square root of -1 is I. You want to break 40 up into perfect squares and the leftovers. 40 is not divisible by anything until you get to 4. 4 times 10 is 40. And now we have the square root of 4, which is 2, and the square root of 10, which can't be simplified anymore. So your answer is 2i square roots of 10. Okay. So what I'd like for you to do is pause your video and try to find the simplified version of the cube root of -27 x to the 9th y to the 7th, and also for number 6, 3x times the square root of 8x to the 4th y to the 3rd. So pause your video and try numbers 4 and 6. So on number 4, pardon my mistake at the beginning. I started writing and then realized I was wrong and needed to scratch it out. That's why you don't do math in pen. On number 4, perhaps you took out the square root of -1 like we did in number 3, which is good that you recognize that when you have a negative, you should take it out. However, in this problem, it's the cube root of everything that's underneath the radical. And the cube root of a negative can happen because I can have -3 times -3 times -3, which is -3 cubed, and that equals -27. So it's possible for me to have a negative radicand under a cube root. So that is a perfect cube. I take out my perfect cubes here. Here's my leftovers. Check your answer. And then on number 6, 3x stays outside. And whenever you have this line and you put together with multiplication the outside, so 3 times 2 is 6, and you have x times x squared, which is x to the power of 3, and a y. These two have odd powers taken out of an even root, so you put absolute value around them. And finally on the front, let's talk about number 5. This is the 4th root. So I really want to take 32 and break it up into factors this way because I want to see what numbers I can find where 4 are the same within 32. So 32 I can break it up into 2 and 16, and 2 and 8, and 2 and 4, and 2 and 2. So I have 1, 2, 3, 4 numbers right here with the leftover of 2. So my 4th root is going to have 2 times 2 times 2 times 2 in it. That's under here. So 2 times 2 is 4, and 8, and then 16. This leftover 2 is going to go here. X to the power of 10 is not divisible by 4. Bump it down until you find something that is. Not 9, but 8 is divisible by 4. And x squared is what's left over. 8 plus 2 is 10. 15 is not divisible by 4. Neither is 14 or 13, but 12 is. And y to the power of 3 is what we need to multiply and get this. 12 plus 3 is 15. And z to the power of 8 is already 8 is already divisible by 4. So the 4th root of 16 is 2, because that's what multiplied by itself 4 times gives me 16. 8 divided by 4 is 2. 12 divided by 4 is 3. 8 divided by 4 is 2, times the 4th root of 2x squared y cubed. This was an even root. Did I take out any odd powers? Yes, I did. This one right here. Okay, so the more practice you participate in, the better you are going to get at these problems. So the next part of our notes has to do with multiplying the radicals. So whenever you multiply radicals, you have to pay attention to whether you have binomials, like here, so 2-term polynomial, or if you just have this single-term monomial times the single-term monomial. When you multiply radicals, if you have something like this, you multiply the numbers on the outside and you multiply the numbers on the inside. So 3 times 2 is 6. Square roots of 6 times 3 is 18. And you always check to see if you can simplify the radical. So 6 is still on the outside. I can break the square root of 18 up into a perfect square and the leftovers. The perfect square that divides 18 is 9. So we have 6 times the square root of 9, which is 3, times the square root of 2. And this is 18 square roots of 2. So why don't you try number 4? Remembering that if you square something in parentheses, that's like writing it 2 times and connecting it with multiplication. So pause your video and try it out. Check to see how you did. Works out really nicely. If you also, instead of doing this, if you just took the squared and applied it here to get 4, and then you squared the square root of 5 and you realize they cancel out and you just get 5, that's still a good way to get the answer of 20. So let's look at what happens if instead of having monomial times monomial, you have binomial times binomial. Well, just like in the last set of notes, whenever we had, instead of radicals, whenever we had complex numbers, you still want to use FOIL. So 3 times 3 is 9. 3 times negative square root of 6 is minus 3 square roots of 6. Positive square root of 6 times 3 is 3 square roots of 6. Notice how the 3 is not under a radical, so it comes in front of the radical. And then finally, the square root of 6 times the negative square root of 6 is minus the square root of 6 squared. So what happens when you square a square root? It goes away. So now we have a 9 and a minus 6. So 9 minus 6 is 3. And we have negative 3 square roots of 6 plus 3 square roots of 6. Since those are the same term with opposite signs, they zero out, and your answer is 3. Let's look at number 3. Because you're squaring a binomial, you want to write the binomial 2 times. Very similar to our last problem, just we have a sign that's different here. So take a moment to FOIL your problem and try to simplify and get your final answer. Pause your video. So in this problem, this line of work probably wasn't too difficult to get. Squaring a square root cancels both of them out, so you're left with plus 6. Notice that negative 3 square roots of 6 minus 3 square roots of 6, you kind of treat it as like terms where the square root of 6 is almost like a variable. So if you have negative 3 of them and you subtract 3 more, you get negative 6 of that same radical. And then 9 plus 6 is the 15 that you see here. So let's look at number 5. This is the last problem that we have like that here. If you FOIL, 2 times 3 is 6. 2 times negative square roots of 3 is minus 2 square roots of 3. 3 times the square root of 8 is 3 square roots of 8. And the square root of 8 times the negative square root of 3 is the negative square root of 8 times 3, which is 24. So, I've got no square roots that are the same type. I've got square root of 3, square root of 8, and square root of 24. Remember that you can break down and simplify radicals. So I'm going to do that with what I can. The square root of 3 can't be broken down anymore. So this is minus 2 square roots of 3. But the square root of 8 can. It can be broken up into the square root of 4 and the square root of 2. And the square root of 24 can. It can be broken up into the square root of 4 and the square root of 6. So now we have the square root of 4, which is 2, and 3 times 2 is 6. We have the square root of 4, which is 2, so this is minus 2 square roots of 6. And there are no more radicals that we can break down, and they're all different. So we consider them not like terms, and we stop. That's as simplified as we can get. So this prompts the next section of our notes about adding and subtracting radicals. The index is the number that's here. So if you're talking about the square root of something, there's an understood index of 2. If you're talking about the cube root of something, the index would be 3. And then underneath is the radicand. So two radical expressions are like radical expressions, kind of like terms, if the indices, which means the plural form of index, so their indices must be the same to add the radicals, and the radicands must be the same. So here, the index is 2. It's an understood 2 because it's a square root. Here the index is also 2, so they have the same index, but the radicands are different. This one's 2, this one's 3. So can we simplify this at all? No. Radicands are different. Look at the next problem. Here, the radicands are both 3. What is this index? 3. What is this index? It's a square root, so it is a 2. Can these two terms be added together? No. The index isn't the same. And then finally, we have 3 square roots of 2 plus 4 square roots of 2 plus 1 square roots of 2. The radicand is 2 on each one. The index is also 2 on each term because it's the square root, so we can add. And when we add the coefficients in front. 3 plus 4 is 7, plus 1 more is 8, and we keep the square root of 2 label. And finally, we've got a fourth example, but it's not printed. Go ahead and write out that if you had the square root of 2 plus 2 square roots of 3 plus the square root of 3, and I wanted to simplify that, well, they all have an index of 2, which is good because they're all square roots, but only these two have the same radicand. So when you combine like terms, this one doesn't combine with anything. It stays visible in your answer. And 2 square roots of 3 plus 1 square root of 3 is 3 square roots of 3. Okay. So what I'd like for you to do is pause your video and try number 4. Check your work. You have to simplify the square root of 8. You have to simplify the square root of 18. You'll find that you have like radicals. So the index is 2, the radicand is 2. We add together the 2 plus 6, and we get a coefficient of 8 with your square root of 2. Number 5 is not multiplication, but we do have to take the subtraction symbol and distribute. So this is 3 plus the square root of 27 minus 2 plus the square root of 3. 3 minus 2 is 1. We can break up the square root of 27. We can make it the square root of 9 and the square root of 3 plus the square root of 3. We have 1 plus the square root of 9 is 3 with the square root of 3. Plus another square roots of 3. These are like radicals. So we have 1 plus 3 square roots of 3 plus 1 square roots of 3 is 4 square roots of 3. And then number 6, pause your video and try it out. All right, go ahead and check it out. Pause your video if you need more time to check. I'm going to move on to the next few problems. These are the last ones that we have. So number 1, I'm actually going to leave to you to do. Number 2, this does not look like something that we have seen. However, this does. Looks like something you should be able to break up and factor, right? So my magic numbers need to multiply to give me 9, but add to give me 6. So 3 and 3. So my factors are x plus 3 and x plus 3. I notice that that can be written as x plus 3 quantity squared. And what did we talk about? When you square a square root, or when you square root a square, those cancel out, and you're left with x plus 3. We did actually take out this is an odd power out of an even root, so we should probably put absolute value around it. And then finally, last question today. You can do this a couple different ways, but I might multiply these two together and then re-break them apart. So 10 times 18 is 180. 2 plus 3 is x to the power of 5. 5 plus 7 is y to the power of 12. I'm going to break this up into perfect squares and the leftovers. I'll go ahead and tell you that 180 is divisible by 36, and it's 36 times 5. X to the 5th is not a perfect square, but x to the 4th is, and x is left over. And y to the power of 12 is a perfect square. So we have the square root of 36, the square root of x to the power of 4, the square root of y to the power of 12, square roots of 5x, and an odd power out of an even root gets absolute value put around it.